Kepler's second law. What was it called?
Law of conservation.
So there are two names for it. One was called the law of conservation of momentum, and the other one was called law of equal areas. Let's talk about the second one first, the law of equal areas. What does that mean? That means if there is a sun here and there is a planet here, most of the time, these, again, this is going to be I'm drawing it outer scale just to show you what it looks like. When you take the areas as this planet goes around the sun, you will see that the closer this is to the star, the larger the speed. And why is that? The reason why that is because Kepler's law says that this area must equal that area. See it? As it goes through, it sweeps out an equal area in equal time. Consider this is 1 month. This is also 1 month. So the time that a planet takes to go from here to here and here to here must be the same. What does that tell you about their speeds? So this must be slow and this must be fast. Right? Because it has to cover more distance over time. And that's what Kepler's law says. That during its motion around the sun, it speeds up and slows down depending on where it is in orbit. This happens because of ellipses. Earth doesn't do much of this because we are almost a circle. So we stay almost constant as we go around the sun. But planets that have more elliptical patterns, they do that. They speed up and then they slow down and they go far away. And that's it doesn't happen very quickly. It's a gradual process. But the reason why it's called the law of equal areas is because it sweeps out equal areas in certain delta t's. So in 1 month, it'll go this far, but in another month, it'll go that far. It all depends on how far away a planet is from the sun at that moment. And they change, right? So we always talk about average distances between the sun and Pluto, the average distance between the sun and Earth, right? It doesn't stay constant. It keeps changing. Does that make sense? So that is why it's called the law of equal areas. Now, the formal definition is a line that connects a planet to the sun sweeps out equal areas in equal intervals of time. Okay. Another thing is the law of conservation of angular momentum. How does angular momentum play a role in all of this scenario? So I'll show you how that works. What is the definition of angular momentum? L equals R cross P, where R is the radius, P is momentum, and P is defined as M times V. So may I write this as R times MV? Okay, so may I also write R times V taking M constant? This is L. May I differentiate with respect to time? What will I get? dl over dt equals m dr over dt times v plus r times dv over dt. What is dr over dt? Velocity. So will I I get this? This is V and this is also V, right?
Yeah.
In vector notation, what is R cross R? Cross product.
Zero.
Yes. They cancel each other out because I unit vector times J unit vector, I times I is 0, right? I unit vector times I unit vector is 0. I dot I is 1, remember? And I dot J is K. Remember those smiley faces I made you draw in chapter 1? There's a reason. Sometimes that's smiley face is what you remember. Anyway, what am I left with? M R cross dV over dt. What is dV over dt? Acceleration. May I write this as R cross F? Because F is MA. Okay, what does that tell me? dl over dt equals R cross F. And what is R cross F? Very good. Who said that? Woohoo. Torque. When things exist in a plane, if I have a plane and things exist on it, and I am doing R cross F, what is my torque? For things existing in a plane, if I do R cross F, torque has to equal 0. This means in a plane, torque has to equal 0. Right? R is in a plane, and the force that's acting on it is in a plane. So what's the angle between R and F? 0. Sine of 0 is 0.
So they can both act in the same plane.
So yes, so the way the solar system or any system is made is that all of them go this way, right? They're all acting in one plane. So R is going in this plane, and the force by which they're attracting them is also in this plane. So what's the angle between R and F? What is the sine? It's a cross product, right? What's the sine of 0? So that means in a plane, torque equals 0.
Yeah.
So what does that give me? dl over dt is 0. And what does that imply about L? There is only one explanation. Angular momentum has to be constant. Because the only time you take a time derivative and it's 0, right? That's what you say, right? Isn't that what Kepler's second law said? It was also called the law of conservation of angular momentum. Did we not just say L is a constant? It doesn't change its value. If it's 3, it will remain 3. Ta-da!